Okay, let's get started. Last 3 classes. We have several announcements. First, we will have our final CTF in the last class, December 6th. So the final CTF will be 120 points. Then there will be a written exam, like what you did for the midterm, but just I want that written exam to be take-home exam. So open book, several questions, so that way you don't have all other homework. Also, I'm looking for students to work on a research project. So if you are interested, let me know. So basically, we're hacking some smart meters. I get 2 smart meters. They are basically embedded devices, IoT devices. We want to study the system security of it, also software security of it. Okay, so last class, we started talking about return-oriented programming. We saw 2 different route examples, and we also started working on a share-code to read a file and print out the file's contents. Hopefully now you can see why the title of the original raw paper is called "The Geometry of Innocent Flesh on the Bone." Okay, because in raw, we chain those innocent bytes together to do something malicious. So it's kind of like you build Legos. So you have Uda Lego, you break it down, then you rebuild data out of that. So that's kind of like what we're doing with ROP. So today we'll keep working on ROP. First, I will show you how to do that share code to read and write files, because I feel that one is quite complicated. So it's better we go through that in class. Then we will look at another even more complicated example. It's not necessarily more complicated, it's a little bit different. After that, we will discuss several defensive techniques to mitigate ROP and other attacks inspired by ROP. Okay, so let me remind you what we're doing here. Our goal is to develop a ROP chain, or we call it a ROP share code. And this share code is supposed to open a secret file, print the content out, and the victim program is a return to libc 64. This is a dynamically linked program, so you can look for gadgets in the executable itself. You can also look for gadgets in the libc library. This is a program. We have been saying this multiple times. Simple main function calls a valful. Valful has a buffer, 4 bytes. So C code level is 4 bytes. If you look at the disassembly, it's also 4 bytes. It opens a local file called exploit, and use that exploit to overflow the buffer. However, the stack is not executable, so you cannot directly inject the share code onto the stack for this one. You can overwrite the return address, you can overwrite the data on the stack, but you cannot put code there directly. Okay, so how do we approach this? How do we develop a ROP chain or ROP share code to hack this victim program? Let's first think about how do we read a file and print it out. So this is a share code we developed in our share code class, right? So to read a file and print it out, the easy way is you just need to make 2 system calls. The first one is the open system call with system call number 5. This one is actually 32-bit. The idea applies. Then you do a system, send a file system call. That one has a system call number 187 there. Okay, so this is a little different from how you program. If you program in C before, you must have been open a file, reading a file, and write a file, right? So usually what you do is you do an open, you do a read, then you do a write. You use a C library call or system call, doesn't matter. So those are three calls: open, read, and write. But here we're choosing an easy route using read and send file. Okay, they're the same. You can do open, read, and write, but it will be more complicated to develop that share code. First of all, when you read, you have to specify a buffer where you store the content of that file you are reading. Okay. But when you do this, send the file, you don't have to do that. You just need to send from one file descriptor to another file descriptor. So we're using this easy route. Okay. So this is how you read a file and print it out. So if we directly want to translate this share code, I even wrote this 32-bit version, but 64-bit will be similar anyway. Even if you want to directly translate that share code or raw share code, it probably looks like the stack will look like this. So you have the buffer. In our case, buffer is only 4 bytes here. Then we have saved RBP. This one is 8 bytes. So you will fill this one with 12 bytes. Then you have the address of several gadgets. So those gadgets are there to set up the registers for you to make the system call. Then you will make the first system call. So you put the system call. There is an instruction. So 64-bit, there is an instruction for syscall. You will put the syscall address here. However, you have to have a return after that syscall. Otherwise, you will never give the control to the next gadgets, right? So you are looking for a gadgets, which is syscall return, okay? Ideally, this will work. Now after this, the control flow, the PC will look for address here, then you set up other registers again for the second system call, which is SIM5. And for the second system call, then after that you do another system call here, and this one technically you don't need the return because you don't have to keep moving, right? There's nothing more we want to do. The problem is you cannot find a gadget like this, okay? A system call return gadget. At least I cannot find it. So let me show you here. So we do a Python. So we can do this first. Yes. Okay, so if we look for the I need to use Python 3 here. So you can say, if I just look for the gadgets in our library, there is no, I cannot even find system call. But we can find the system call in the C library. We can check by the C library we're using. So I use LDV. It tells me which C library it loads when this program runs on this. This is the library, and it also tells me the offset of this library when it is loaded into the memory space. So this offset is also important here. So we look for the gadgets here. Then we can say we can find a lot of gadgets with syscall. So some of them could be originally that system, or some of them may not. But you do not find a syscall return gadget. You just let's see. So we scroll up, you can scroll up here. There's no such gadget. All those gadgets end with syscall. There's no return after that. Okay. So because of that, this approach will not work because we cannot find the gadget we want. So what we can do instead of this is, so every system call, there is a C wrapper. There is a C library function wraps up the system call, which do the same thing. So instead of making the system call directly in our share code, we can do a return to libc. And it works because you do a return to libc, you call a C library function, and at the end of the C library function, there is always a return. And that return will retrieve something from the stack. So you go back to your stack, and you can still control the control flow. Okay? So in this case, what we're going to do is, at least for the first system call, the open system call, we're not going to directly make a system call, we're going to make a library call. For the second one, actually doesn't matter. We can make a system call or a library call. Then this is the function call convention. So we need to put the string secret address in RDI, then RSI just set 0. Then after that, make the system call. The return value will be in RAX. Then for the second system call, the first one is function. Then for the second function call, then the first argument is also in RDI. Then the return value, which is the file descriptor of the file you opened, we'll have to move it from RAX to RSI. Then RDX will be 0, RCX will be some number. So this is the bytes you want to send. So it doesn't have to be 1,000. Okay, so that's why our stack should look like something like this. We first have many gadgets to set up the registers for the open 64. This is 64-bit open 64 function call. Then we have some gadgets to set up for the second function call or library call, and it's a send file 64. And we're not putting any code on the stack on this. Okay, so those are the commands you can use to find those gadgets. The first one is you use LDB to find out where those libraries are loaded. Then the output of the first command, LDB, you will put here, the offset. Without this one, you are only getting the offset of that gadget in that file. And if you say the offset, this is actually base for that library, then you can get the runtime address of that gadget. After that, you can just do grep to search for the different instructions, the gadgets you want. Okay, then here I have I developed this rawshare code. So let's go through it line by line to see how it works. First, I use GDB to find out those two function address, the send file 64 and the open 64. I also find out where is the data section of this program. So that is an area I can write something there. The very first line, we first have 12 bytes of garbage to fill these parts. Okay. And this is the first return address we want to overwrite. There we put the gadget address pop RDI return because we want to set the value of RDI. Then we set the value of RDI of the data section address. So that is the data section is somewhere we can write to. We set that address to RDI, but we haven't put the data there yet. We haven't put the string secret there. So next, we're going to put the string there. What we do is we have another gadget, pop RAX return. And after that, we have the string secret. So what this gadget will do is we'll pop this one into RAX. So after we exit that, RAX will have the value dot slash secret, not the address, the value, the string of it, okay? Then we find another gadget, move RAX to the memory location RDI. So this is where we actually put the value of secret, the string secret, onto that data section. Okay. So after that, now we do have RDI points to the string. Then the next one we need to set up RSI. That's it. So RSI we only want to set up to 0. Okay. So you can see if you want to set up any register, the only gadgets you need is pop that register return, then you put whatever value above that, higher than that. That's how you set a register. But you do not find the gadget to set all the registers. Sometimes you just can't find it. This one we don't have to because there was already one. So that memory location is 0. You can say later, this instruction can say we didn't initialize that one because it was originally 0. We can say that later, okay? So, but sometimes you do not, for example, if you want to set up ECX, RCX, we do find it. Let's say we want to set up R13, and there is no gadgets to do that. There's no pop R13 return, but there maybe is a move R13 RAX return. You can find something. So you just change several gadgets together to get what you want. So after this, we set up this, then we just do return to open64. Okay. So this is what the stack looks like. The address of pop RDI, address of data, address of pop RAX, the value string, those gadgets. Okay. So after this, then RAX in this case, open64 here after it returns, RAX will have the file descriptor number. Usually it will be number 4 because 0 is std in, 1 is std out, 2 is std error, there will be another one. So it could be, usually it will return 4. But that is in RAX. So the next thing you want to do is you want to move the value in RAX to RSI. So you will look for gadgets like move RSI RAX. However, you cannot find a gadget like that. Let me show you. So we're looking at the library. So we look for gadgets, move RSI. RSI, RAX. Okay, you can see at least for return-oriented programming, this is jump-oriented programming, you do not find a gadget like that. And you notice here, some of the gadgets, they end up with a jump. Some of the gadgets end up with call. So this one is a call. So those are called jump-oriented programming or call-oriented programming. That's an extension to return-oriented programming. And we're not talking about those. Obviously, they can be chained together, but we're not talking about those in this class. So the return one, let's see a return one. Oh, this one. Okay, so this is the one I choose to use. You first move RAX to RSI, then you will shift right. EAX shift that to 3 bits, which means, for example, EAX was 8. After 3 shift, it will be 0 or 1, whatever. Right? However, when we run this instruction, when we debug, you can say the value of ECX was 0. So no matter how you shift, ECX will still be 0. Okay. Then after that, we will do a repeat movement, move data from where RSI points to where RDI points to. However, how many times we move depends on value of ECX. So every time you move, ECX will decrement. However, since this one was actually 0 at the beginning, this instruction will never be executed. So for us, those 2 instructions are kind of like NOP. So it doesn't really do any damage to us. Then we have a return. So this one works. So this is a gadget we want. If you cannot find a gadget like this, there may be other gadgets you can. That's where you need to be creative. Think about how to chain different gadgets together to get what you want. Okay, so after this one, we move the file descriptor from RAX to RSI. Then the next one is we will set up RDI. Oh, here. The RDI is 1. That's a file descriptor, STD out. That's why it's 1. So we set RDI as 1. Then we're going to set RDX, this one. We won't set it to 0. Then you see the same problem again. You do not find a gadget to just do pop so the perfect gadget for you will be just a pop, RDI, and return, right? But we find one. That's interesting. No, RDX. No, RDI. So those one were balanced stack, so it's a little different. So technically, this one we can make it work as well. Anyway, we do not find that directly pop RDX return instruction, but I do find another gadget there, which is R12. Syntax. So I do find a gadget like this, pop RDX, then pop R12 return. So this gadget will set RDX and R12. We don't care about the value in R12, so we can use this gadget. However, because there are 2 pops, that's why we need to put 2 values here. One, the value for RDX, which is 0, another value 1 here for R12. the spec is already added. Okay, that's because we only have a gadget like that.
Is there any way that we could represent the situation that I only want the off RDX? I don't care what's after that. I only want to return RDX. So, yeah, yeah, this is exactly.
This is exactly what we're talking about.
Yeah,
right?
but I
We
don't,
only care about this.
yeah, but when I'm searching, is there any way that I don't know R12 at the beginning, so is there any way that I just ignore it, whatever it is, it's fine, so I just want the head and the end.
Well, no, you cannot just ignore that. For example, here, without this one, if you do not put one here, then what you're going to put here is the address of pop RCX, right? Okay. Then when this piece of code executes, 0 will go to RDX. The address of this gadget will go to R12. Then do a return, there will be another, maybe a garbage, there will be actually, there will be 80. 80 will be put in PC. Then the program crash, right? So that's why you have to consider what's going on here. Why this is random register?
Like if you wanted to find the top RDX and then return, like the R12 is arbitrary. Like if there was no R12 instruction.
Yes. I didn't really search R12. What I searched was you can write a regular expression to do pop RDX and whatever in the middle return, right? Then, oh, okay. Okay. Then you can get a lot of instructions and choose the one you feel is the best. So after that, we just need to set up RCX. So here, I put 1,000 there, but in my share code it was actually 80. Then after that, we just put the address of send file. I do have 3 more gadgets to exit gracefully here. What this does is to pump a value to RAX. That 60 is the exit system call. Then you will not crash the program. Okay. So if we debug this program, so to build this, what you need to do is, I think I will build that so we can directly debug this program. And we'll return. So we set a breakpoint and the valve full. Then we just run. So we're in valve full right now. So we just running the program. So F open, just skip that. We will get to return. Okay. Now we are in return. This one is supposed to return to our first gadget. You can say that's our first gadget. Pop RDI return. So we keep doing that. We're going to our second gadget, pop AX return. So if you go to here, you can see pop RDX, pop RAX. Those are our gadgets. Keep doing, and you can see that we are jumping into the middle of some C library functions. Those are the function names. We jump to the middle of those. Now we are making our first function call, open64. So we can do finish. We don't have to debug this one because that's not really part of our rawshare code. So we do finish. So we get out of that function. Now we are in our another gadget, the complicated one, the move RAX to RSI. But now we can say the value of RAX. Let's see. The value of RAX is 4. That's a fire descriptor number. So if we keep moving, more gadgets. Here's some gadgets. Which one's the gadget? Oh, now we're in some file. Then after we do finish, we're supposed to print out the value somewhere. Here. We actually already print out the value of the content because we finished the same file. So this is how this raw gadget works. If we keep running this program, do exit gracefully. There's no crash because I have our exit system code. A problem we have here is if you directly run this without that GDB, sometimes you get it, sometimes you don't get it. Sometimes the program exits before it has a chance to print it out, so you do not see it. But this time we do see it, so it's not a problem. Okay, so that is our first example. Any questions? Oh, that's part of grep, actually. Well, first you can use grep to do that. Also, the raw gadget tool we're using, it also has Python 3. Let's see. The tool we're using, it can also help you find the gadget. For example, the only move return. I think this one helps you find gadgets that has a move and a return, or move or return. I'm not sure. If this one cannot do a job, then you can just use a grep to do the job. Okay, this is the second example we're going to say. So this example, I designed this specifically to ask you to use a specific gadget. That's why it's a little bit weird here. We have the val foo, which takes one argument. There is a 200 bytes buffer. It also reads input from exploit. Then, whatever you input in the buffer, your input is buffer. So you cannot directly overflow that buffer because this code is only reading 190 bytes from that exploit file. However, the buffer is 200 bytes. So you cannot directly overflow the return address. However, the program here does do that explicitly. So this is 32, we're doing 32-bit. So the first 4 bytes, whatever you input, the first 4 bytes will be moved to the return address. That's what this line of code is doing. I also said the global variable here A, but I guess that's, I remember why I did that. Your buffer can be, whatever your input can be as big as 190 bytes. The first 4 bytes will be using to override the return address of this evolve function. The second 4 bytes will be put in the register AEX. EAX. So everything here is just to do that. Okay. So this program stack is not executable. Also, you cannot directly overflow it anyway. Then how can we use ROP to get a share from this? So exactly. So what we're going to do is we find a gadget named exchange. We find a gadget named exchange EAX and RSP. Then there is a gadget like that. Okay. So what we're going to do is we can set the return address. We can also, then the return address will set to where this gadget is, right? Then before that return address, we already put RAX. We can control RAX. Actually, it's EAX. We already have EAX set up. Then we swap the value of EAX and ESP. Actually, we don't need to swap them. We just want to set ESP. But we don't have a gadget to do that. We only have a gadget to swap. Then after that, the ESP can point to our buffer, which we controls. Then on that buffer, we can have more addresses of different gadgets. Okay, so this is what our shared code look like. We will go through this once, and later you will do this by yourself. So the first, remember there are two items in our buffer. The first 2 bytes is going to be the return address. The second 4 bytes will be whatever put in the AX. Okay, that's why the first 4 bytes we put. This is 32-bit, so 4 bytes. The first 4 bytes we put the address of that exchange gadget there. Then the second 4 bytes, the value will be moved to EAX by the program. So once we start executing the exchange gadget, the EAX value is already this one, which is the stack value. Actually, what we do is we put whatever here. This is a piece of code. It's addressing, but this is on stack. Then after that, things will be much easier. We will just set up registers, then do exe setrdi system call, which is at the end we do int 80, which is a system call 32-bit, and the system call number is b, which is exe setrdi. So everything before that, we're just setting up. We're just setting up those registers. Okay. So this is a template I gave you. So later in the class, you need to find the address of all those gadgets to make this code work. Any questions? Good. Okay, now we talk about the interesting part. So ROP was developed back in 2007, 8. Yeah. Then after that, people realize we can generate generalize this one, especially to find out as long as there are indirect branch instructions, we can chain them together, build something similar to raw. So the return instruction we use in raw, that is an indirect jump instruction. It's indirect because the target where you are returning to is not hard coded in that instruction itself. The address is on stack, and stack can be compromised. There are other indirect branch instructions, for example, indirect call or indirect jump. For example, if there's a call EAX, that's an indirect call. If it's a call a fixed address, that's a direct call. So two more types of tags were developed. One is called call, return or call oriented programming. Another one is called jump oriented programming. That's why you see the log tool we're using, the log gadget tool we're using, it helps us to find those gadgets as well. So how do we defeat this kind of attacks? So those were proposed like 10 years ago, and the systems we're using nowadays, they have all kinds of mechanisms to defeat those attacks. So like everything, all the attacks we saw before, if you think about how to defeat them, it's not very difficult. You can see, I'm going to show you many papers, you can see those ideas are very simple. Okay, everyone can come up with those ideas. What you need to do is, for every attack or a class of vulnerabilities, you need to think about what are the conditions to pull off this attack. For example, this drop attack, first, at least 5 different conditions here. So all those conditions have to meet, so you can pull off this attack. The first one is you need to be able to subvert the control flow, at least to the first gadget. Okay. So for example, the vol we looked at before, you still need to override that return address of that vol. After that, things will be easier. Then you still need to control the content on the stack. Even though you don't have to inject code there, but you are putting data out there to control the control flow there. That's a second condition. The third condition, you need to have enough gadgets in the address space. The fourth one, you need to know the addresses of those gadgets. Also, this one, people were forget about this. Actually, you also need to start execution anywhere. If there's a gadget, you should be able to execute that gadget. And that gadget could be middle of a legit instruction. You should be able to execute from there. Okay. So in the last almost 10 years, there are many approaches try to take one or several conditions out, so attackers cannot do this attack. The first defense technique we already started is shadowstack. Because shadowstack can protect the return address on the stack. So if we have a shadowstack, you cannot even subvert the very first control flow. You cannot even give the control to your first gadget. Right? So that's a shadowstack. However, shadowstack only protects what we call is a backward edge. There is a more generic version to protect forward and the backward edge is the technique called control flow integrity. As you can see, the name is very generic. It tries to maintain the integrity of a program's control flow. And that control flow is determined at compiler time or link time, and that integrity is enforced at runtime. This is a very comprehensive approach, however, very difficult to implement. Also, the overhead is very high, even if you implement it correctly. However, sometimes it's just very difficult to implement because typically static analysis, you have to offline, you have to build a legit control flow graph. But building a legit control flow graph with indirect jump calls is very difficult. So that's why even though this paper was published before ROC. ROC was 2008, and the CFI was 2005. And CFI can protect all kinds of attacks from happening, including ROC. At a high level, CFI restricts the control flow of a program to legit, valid execution traces. It enforces this property by monitor the program at runtime, compare its state to a set of pre-computed valid states. So all CFI mechanisms mainly consist of two components. One is usually a static analysis component. Static analysis means it's kind of like part of compiler. If you have source code. If you don't have source code, obviously it's not a compiler, but it's still some kind of program analysis approach. Static approach to build the control flow graph of the application. But the control flow graph here we're talking about, I'm meaning about those indirect calls, indirect jumps, not those direct ones. The direct ones are easy to build, but we don't need to protect direct jumps. So why we don't need to protect the direct jump or calls in a program? At least we do not protect them from ROC or overflow. Yeah, because for direct calls, the target of a call is embedded in that instruction. And that is part of the code. It's in a non-writable memory address. As long as we maintain this whole code section is not writable, we don't need to worry about its control flow can be something, or it cannot be. However, yes. So the static analysis part is supposed to compute for each indirect jump or call the set of valid targets. But that is very difficult because that's static analysis. Static analysis is always difficult, sometimes not complete. But that's the idea. So static analysis compute for each indirect call jump, those are the valid targets. Then at runtime, whenever there is a jump, then we compare if this is a valid target in that set. Yeah. So the runtime module, just like I said, we're just to compare each time if there's a direct indirect call. So a little bit background here, what is direct call, what is indirect call? If you read a paper in this area and you see those terms, it could be a little bit overwhelming. So direct call, direct jump, basically is an instruction with a fixed address as the argument, and the address is part of the instruction. For example, we can use route 2 as the example. So this is route 2, and in route 2, we have this main function. The main function will call two functions. We'll call this function, and also we'll call both. So those two calls, they are direct calls because the target is hard-coded in the instruction. For example, this call is called this address. It doesn't show here because in this encoding, it only encodes the target's offset relative address to the current address. This one is E814, so no, the E8 is the opcode. So this part is actually the relative address. So this one looks like a negative number, right? Because of F. So this is a negative number. That's why the target is the current address 92FD minus something. That's why our real target is 9216. Okay, but the target is hard coded in this instruction. The same thing here. Same thing here. However, where is our indirect code on? Which one have we here? Okay. Here we have another C program. The C program, it has a main function. The main function will take the input from the user. So at compile time, you don't know what is the input. Only runtime you will know what is the input. Then you will call the full function using that user input. And the full function first has a function pointer. Depends on what the user's input is, the function pointer will point to two different functions, either bar or bands. Then it will call that function. So at compile time, there's no way to tell which function you're actually calling because it's determined at the runtime. So if you look at the if we look at the disassembly of this program, you can see there is a call EAX, and that is an indirect call because the value of EAX is only determined at runtime. And you can say, depends on what the user input, it will set up either EAX, either this one or another value. Yeah. So 32 version, 64-bit version, the same thing. Also, the function return, like I said, is also an indirect jump because the target is not hard-coded in the code section. So even if the code integrity is maintained, the control flow integrity cannot be maintained. So in all the literature, we call those call or jump was the forward edge. And the backward edge is used to return to a location that was used earlier in a forward edge. Basically, means the return instruction. So back to our example here. This call is a forward edge to call a function. And this return is a backward edge to the function that calls the full function. So things can get much more complicated if we also consider interrupts and the interrupt returns. Because so far, meanwhile, we're talking about still at the username level. We're not really touching kernel. But if you consider a real system, kernel also has many issues, and the interrupt can happen anytime. The integrity, control flow integrity of interrupt also need to be maintained. Using the same example, I will show you where do we enforce control flow integrity. This is the code I just showed you. We have this full function, which has a function pointer. The function pointer also has the information of the function prototype. This prototype of this functions, it doesn't take any parameters and it doesn't return anything. That's why it's void here and also void here, right? Then this function pointer at runtime can be set to either bar or max. It looks very simple here. If you read the code, it looks like that's the only two possible values. But for static analysis, for compilers or program analysis tools, to analyze very complicated programs, to identify what are the possible values for this function pointer is very difficult. Okay. In this example, it looks very simple, but in real-world programs, very complicated. This problem is very, very difficult. Then, whenever we make this function call, we can inject some enforcement code here. So the enforcement code, before you make this call, the enforcement will decide if that function call is valid. Then there are many different policies, depending on how accurate your static analysis tools are. For example, one of the policy is this function call, this is a forward call. You can call to any function. As long as you call to any function, that is allowed. Then in this example, there are 4 different functions. Now, another one is you have to call into a function with the same prototype. Then 3 are allowed. Then the most accurate one is you should only call into the function that based on by reading this, because those are the only 2 possible legitimate functions. Or like I said, this is really hard to compute. Then this is a forward, and every time the function returns, we'll also do a backward edge check. And this part is what we started before, the shadowstack. So whenever people talking about CFI, they're talking about 2 different things. One is the forward edge integrity, another one is backward edge integrity. And the backward edge integrity is what we discussed before. Shadowstack can do that. There are several other approaches can do that. So that's the first defense direction. Basically, you make sure that the attacker cannot subvert the control flow. And this is the most solid defense, however, very expensive, hard to implement. The second approach to defeat rawshare, those attacks is another approach we are very familiar with, is address-based layout randomization. So we already know that this approach is not perfect. We had an example to bypass this before, right? However, in all our examples, we disable the ASLR. Even if we enable that, it's possible we can hack it. This approach basically randomize the gadgets, it will randomize the libraries, everything. So it will be harder for the attackers to know the address of the gadgets. you sure you didn't disable that? It should not work. Because you have those gadgets address here, right? And every time you run that the target program, the gadgets address will be changed. So it should not work. How do you know you didn't disable it? Are you sure you didn't disable it? Which homework we're talking about? The first one is to get a share, right? Yeah, that one should not work. So anyone else who didn't disable ASR? Yeah. Okay, let me take a look. It worked for you? Okay, let me take a look. Last week's homework. The only explanation is the gadgets, they didn't move, right? As long as they moved, your program will just crash. Somehow they didn't move. I don't know why they didn't move. So for you guys, you didn't disable SR, but did you check the address of those gadgets? Yes. So why do they remain the same? Well, as long as they remain the same, obviously your share code works. But I don't know why they remain the same. Because what did you say? So we did it twice. Once in GDB, one also. Well, the GDB doesn't matter here. Because we're not injecting code to GDB. So even though the offset of the stack will change a little bit, but that doesn't matter. What matters is the gadgets address. Why those gadgets address don't move. That's why you have to add the offset there. That's weird. Okay, I'm not sure what's going on there. I will check the homework and debug a little bit there. Well, it's possible that, I'm not sure about that one. I will take a look later. Okay, so the second difference is ASSR, which moves the gadgets around so you can use them. The third approach, which there was a paper published almost 40 years ago. The idea of this paper is to remove the gadgets. So if in our address space there are not enough gadgets to use, then obviously we cannot do drop or top. This one was not published in the top value, but still a very good conference. AXAC is one of the good system and software security conferences. So we said this last week. So those return instructions, basically at byte level, they're just those values. Say 2, say 8, say 3, say 8, those 4 values, at least the 32-bit version. So if there is no those values in your memory, then there is no return instructions. So the idea is very simple. Whenever we say C3, C2 in any part of an instruction, we just change that instruction. We change that instruction to an equivalent instruction without those numbers. For example, this jump instruction, jump to relative address say 8, because this instruction itself, I think it's 5 bytes. That's why when this one is compiled, the actual binary code bytes are E9, that's jump. So this is offset C3. That's why there is a C3, right? So if the compiler is going to generate an instruction like this, you will change it to something like this. You will jump to the next instruction and log there. So by doing this, the stage 3 doesn't exist anymore. The stage 3 will change to stage 4. Okay. So if you look for gadgets or return gadgets, this will not be a return gadget. Right. Very simple idea. Other examples, if you do add C2 to EX, then C2 will be interpreted as a return, right? So we replace this instruction with 2 instructions. We add C1 to EX, then we increase EX. Equivalent instructions without C2. Same thing here. This one has a CA, which we want to get rid of. Then we have a different instruction. Another example here, we move memory location EBP minus 38 to AL. And this one will have a CA at the end, which just changes to an equivalent instruction. So that's a basic idea. So this paper tries to remove the gadgets, every gadget in the address space. Another one is to monitor the CFI. Actually, this one. So the idea of this one is implemented in modern CPUs. At the very beginning of the class, you already see this instruction, end BR32 or end BR64. We see a lot of those. And in the first half of the class, I ask you just to ignore that. Okay? So what this instruction does is, for latest CPUs, this is just a feature to for CFI. For older CPUs, this one is equivalent to a log, doesn't do anything. Okay? For new CPUs, how this works is all the indirect calls, call EAX, the target has to be this instruction. This feature is implemented in Intel CPUs and also ARM CPUs. ARM CPU, I think this is called a BTI or BIT, branch indirect tracking, maybe BTI. Anyway, so you can see this is a weak form of CFI we talked about. But this can be very fast. This is a weak form of CFI like the first version. So for any indirect function call, as long as the target is a function, that is allowed. That's why at the very beginning of every function, we have that instruction. in the CPU, internally, there is a state machine. If the state right now is an indirect call, the next target is not an the BR instruction, then you generate a fault. Generate a fault. That is how it works. That's why we're missing a lot of those instructions. Right. There are other defense. This one is also interesting. In modern CPUs, there are tracing units that can record what instructions have been executed. Then there are approaches that just to what do we want to copy? When did we copy any instruction? Remember, this is a code section, right? This is not relevant. That works, but the chance you have, well, let's say that NBR32 is like legit landing pad, right? And there are, so all the functions in this memory space, they have this legit landing pad. And you are saying that it's possible there are other legit landing pads in the middle of functions, but just randomly it's there, right? Okay, that could happen, but the chance of that is very small because that's 4 bytes. For 64-bit, I think it's maybe even longer, not 4 bytes. And the chance to have that, have some random data or middle of the part of the instruction to match that 4 byte is really small. But yeah, even if sometimes you find that, that does not necessarily give you a valid, a very useful gadget. Yeah, that's possible. Yeah. Okay, going back to this one. So other approaches is the CPU will just monitor what instructions have been executed recently for the last 50 instructions. How many of them are returned? So for legit functions, you can say for 50 instructions, the chance you have maybe 2, 3, you may have 2, 3 return instructions, but maybe not more than that. But if the CPU have been executing 20 instructions and 8 of them is a return, that's obviously a red flag. You can see the gadgets we're using there, they're quite small. Just several, the longest we have is like 3 instructions plus return. Most of them are just 1 instruction plus return, right? So then if the percentage of return instructions are very high, then it's very likely that's a raw attack. So that is another approach to deflate this. But you can see those approaches, they do not really guarantee to deflate raw. And also, the only one that guarantees everything is setup. However, it's very difficult to make it right. Okay, so actually, my team, we are also working on something CFI very low end devices using different tracing units. We're talking about the Cortex-M devices. The approach we are using is similar to this one, but very low end device. So this one I'm talking about Intel devices. Okay, that's all I have today. Any questions there? it's possible that the computer you're using, the CPU doesn't support it. I'm not sure if you have to enable some feature in BIOS to enable this feature, but well, the short answer is because right now your CPU is not using that feature. I don't know if it's because your CPU doesn't have that feature or it's not enabled. It's probably because it's not enabled by default. The technique, Intel, they call it CET. It's called Intel CET. I don't know if it's enabled by default. You can go search. That's a good question. I never looked into that. Okay, so, okay. So first of all, you need to, when you compile a program, you need to specify some flags to enable that. Eventually it's a CPU. Eventually it's a CPU, but maybe the CPU, no, well, maybe the kernel will look at your program to say if the program wants this feature. If the program wants a feature, the kernel will enable the CPU to do that. Otherwise, it will not. So eventually, it's determined by the CPU. It's if this feature is not enabled, then the CPU doesn't care where those indirect jump or indirect more like a return goes to. I don't care. Oh, and another issue is what we're doing here is like a ROP, right? So ROP is not an indirect call. It's a return. The return will always go to the middle of a function anyway. So that one, I think, mainly works for forward edge. Because it's at the beginning of the function, right? So it's always calling to that. So that's for forward edge. So what we are doing for ROP is backward edge. So even that feature, even if that feature is enabled, it will not be able to protect our attack. Our attack will be protected by shadowstack. Yeah. However, the Intel CET technology does include both forward edge protection and backward edge protection. I'm not sure how about the backward edge works. Maybe it has to. I think it's probably more like acceleration optimization, but the compiler has to utilize that feature. I'm not that familiar with Intel right now. Okay. Okay, that's what I have for the lecture. So what we're going to do next is you're going to finish both of the exercise. The first one is to share code read and write. The next one is get a share from log 2. I give you the template. I already put everything on my website so you can download it. So this is also your homework, but you can start working on this here. So if you have any problems, questions, I can help you. I will send you the
그럼요. Or Monday, our classes on Monday, right?
No, I know. I was asking.
Okay. Yeah, I think I checked the calendar. I don't think we are going to skip that. Yeah. it's not showing.
I just searched to enable that entire set feature for Ubuntu. You need to compile your program using stack clash protection and also CF protection. Right. So when I compile the programs, I didn't use those two flags. That's why the CET feature is not used. Yeah, you can. So the example you said there, you can try to recompile with this and try again. See if it works.
I think after one, so